Alright guys, welcome to lesson number 4 for unit 1. We're going to jump a little ahead to electron configurations. Okay, so this is a brand new topic. In the previous lessons, we have talked about the different atomic theories, and Bohr model is one of it. And we've learned how to find the number of protons, neutrons, electrons using atomic mass and atomic numbers. We've talked about isotopes, how neutrons are able to change. And now we're going to go back a little bit and return to the Bohr model. And we're going to learn how to draw those Bohr models, okay? So essentially, Bohr model have a few rules that you have to follow, and one of them is the electron configuration. Okay, so learning the electron configurations will teach us or give us instructions on how to draw a proper Bohr model. So let's look at this. So for electron configurations, to write the full electron configuration of any element, the diagonal rule must be followed. So you probably don't know any of this right now, but it's okay. This is our first lesson on this topic. In the next lesson, I will explain more about this, okay? So for now, just tag along. So for electron configuration, the main word right here is electron, right? So we're focusing on electrons this time. We don't really care about the number of protons. We don't care about the number of neutrons. We just care about the electrons, okay? So right here, we have 1, 2, 3, 4, all the way to 7s. So for the off-ball principle, we have to, there are 4 different orbitals or 4 different blocks on the periodic table. So for now, just follow along with me, and in the next lesson, I will connect you from here to the periodic table. So right now we have this 1, 2, 3, 4, all the way to 7s, and then we have 2 to 7p, and then we have 3 to 6d, and 4 to 5f. Okay, so this is the general table that we have to follow, and then there's a diagonal rule. So for the diagonal rule, you're gonna have to go through 1s first. After the 1s, we're going across 2s, and then after 2s, we're going into 2p and 3s, and after 2p and 3s, we're going through 3p and 4s. After that, we're going through 3d, 4p, 5s, and you get the hang of it. Next one would be 4d, 5p, 6s, and then 4f, 5d, 6p, 7s, and the last one, we have 5f, 6d, and 7p. So as of right now, we only have 7p, and we don't have 8s because we don't have that many elements. But it could grow in the future. Okay, so right here, these ones right here, those are the energy levels. Okay, so the 1s will have 1 ring or 1 circle. All the 2s, the 2s and 2p, they have 2 circles. There's circle number 2. Okay, that's level 1. This is level 2. And then all the 3s, p, and d, that's our circle number 3. Let me change to a different color. And then once we get to 4, we have 4s, p, d, and f. That's our circle number 4, energy level 4. Okay, so all of these numbers in the front, 1, 2, 3, all the way to 7, those are just the amount of energy level. Okay, that's it. So whichever number it is on, that's which energy level it is on, the circles. And there's a specific amount of electrons each of these orbitals can hold. So we have energy level 1, 2, 3, 4, 5, 6, 7, and then all the s orbitals are able to hold 2 electrons, and just 2. It cannot hold more than 2. All the p orbitals can hold 6, and then all the d orbitals can hold 10, and f can hold 14. So for right now, just remember it. I will explain to you in more details next lesson. So these orbitals can hold less. So this one, the s, can hold 1 or 2, but it cannot hold more than 2. Same thing for p, it can hold from 1, 2, 3, 4, 5, or 6, but it cannot hold more than 6, okay? Same thing for d and f. So that's the rule. Next one, for example, let's try this. We have copper, okay? So copper, if we look on the periodic table, it is number 29. So that means it has 29 protons and also 29 electrons. We're only looking at the electrons, okay? So we need to get to 29 electrons. So our goal is 29. 29. Okay, so following the diagonal rule, the first one we're going through is 1s. And remember, s can only hold up to 2 electrons. 2. And that's it. So after I'm done with this one, I'm going to move on to the next one. So 2s is my next one. So 2s, again, this is s again. I can only hold 2. And then next one would be 2p. Okay, so 2p is the next one, and p can hold up to 6. So now I have done 2, 2, and 6. That's a total of 10. My goal is 29. I need 19 more. So let's keep on going. We're going from 2p all the way to 3s. 3s can hold 2 again. And then next one is 3p. 3p can hold 6. So that's 10 plus 2, that's 12, plus 6, that's 18. I still need 11 more. So after 3p, I'm going into 4s. So 4s can hold 2 electrons, right? So that's 20. So I need 9 more. So after 4s, I can go to 3d. So 3d. 3d, remember, d can hold up to 10 electrons. And I need how many? I need 29. And I've already gotten 20 up here, right? So 2 plus 2 plus 6 plus 2 plus 6 plus 2. That's 20. I don't need all 10. I just need 9. So it will end at 3d9. Does that make sense? So here is the full electron configuration for copper. So the 1, 2, 3, and 4, those big numbers are the energy level, okay? And the small numbers right here, we'll have 2, 2, 6, 2, 6, 2, and 9. Those are called the superscripts, okay? So whenever you have a number that is on the top, a number like 2 right here, normally in math you call it exponents, right? Or power, but in chemistry we'll call it superscript. So the superscript is on the top. If you have a number down here at bottom, that's called the subscript. Okay, so basically this one is on the top, super is on top, sub is on the bottom. So if you learn about physio or physiology, you're going to learn about medical terms, right? So superior is on the top or above. Okay, too much off task. So right here, those superscripts are the number of electrons in the orbital. So total, we have 2 plus 2 plus 6 plus 2 plus 6 plus 2 plus 9. And that will give us 29, which is the amount that copper needs. So this is the electron configuration for copper. Okay, so this is how you write electron configuration, and we're going to use this to help us draw the energy level, the Bohr model. Okay, so right here, the big numbers in the front, we have 1, and then we have energy level 2 with all the 2's in the front, and then energy level 3 is all the 3's. Right here we have 3s, 3p, and 3d, and then 4 is energy level 4. So copper obviously will have 4 energy levels. Okay, and to draw the Bohr model for copper, it would look like this. Let me change a different color. So 1s2, that means my energy level 1 will have 2 dots. So the first circle, I will have 2 dots. 1, 2. 1, 2. That's 2 dots. And then my energy level 2 will have 2s2. So 1, 2. And then I have 2p6. So even though it's a different orbit or orbital, it's still on the second energy level. So I will just add 6 more. 1, 2, 3, 4, 5, 6. Okay, and then my energy level 3, I will have 3s2, 1, 2. And then 3p have 6. I'll add 6 more. 1, 2, 3, 4, 5, 6. And then next one, I have 4s2. So this is energy level 4 or circle number 4. I'll add 2 dots. And then right here, I'm going back to 3d9. So I will go back to energy level 3 and draw 9 more dots. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so this would be the Bohr model of copper. So it looks pretty simple. There's just a few rules that you have to follow. Okay, so let's look at more explanation. So for example, right here we have nitrogen, right? Nitrogen has, well, on the periodic table, it would need 7 electrons total. Oops, that's too big. 7 electrons. So right here we have 2, 2, and 3. So that's exactly 7. And that is the electron configuration of nitrogen. Okay, so nitrogen have 1s2, 2s2, and 2p3. And we're stopping at 2p3. That means a nitrogen will only have 2 energy levels, which is correct. So right here, nitrogen have energy level 1 and then energy level 2. Okay, and then on energy level number 1, I have 2 dots or 2 electrons on there. So that's why there are 2 blue electrons right there for s orbital. And the second energy level, I have 2s2. So these 2 blue dots are the s orbital electrons in level 2. And then I have 2p3. So these 3 green dots are the p orbital in level 2. So total, there are 7 electrons or 7 dots on this model. So this is the Bohr model of nitrogen. All right. Next one, electron configuration. Again, explanation. So the number in the front, the first number in the front, that tells you what energy level it is on. The S or P or D or F, those tells you the orbital or shell block. And then the superscript on the top, it tells you the amount of electrons. So remember these numbers. S can hold up to 2. P can hold up to 6. D can hold up to 10. And then F can hold up to 14. All right. So next lesson, I'll give you an easier way to remember this. But for now, pure memorization. Because I just want you to learn this right now. But when we connect it to the periodic table, it's much easier. Now, let's look at this example. We have the electron configuration done for aluminum already. So aluminum has an atomic number of 13. That means I will also have 13 electrons. 13 electrons. So this is the electron configuration of aluminum. So I have Al 1s2, that's 2 electrons, plus 2s2, that's another 2, plus 2p6, that's another 6, 3s2, that's 2 more, and then p1 plus 1. So total adds up to 13. So this is our electron configuration for aluminum. So to draw the Bohr model for aluminum, it would look something like this. So energy level 1, energy level 2, the two big numbers in the front, and then the 3s, those are shell or energy level 3. And energy level 1, energy level 2, and energy level 3. So now all we have to do is fill in the dots. Okay, so to fill the dots in for my first energy level, I only have 2 dots. So 1, 2. My second energy level, I have 2s2 and 2p6. So a total of 8. I'm going to draw 1, 2, 3, 4, 5, 6, 7, 8 dots. Okay, it doesn't really matter where you put the dot. And then the last energy level, I have energy level 3. That will be 3s2 and 3p1. So total of 3, 1, 2, and 3. This is my Bohr model for aluminum. Okay, so this is how we use electron configuration and how to draw the Bohr model with it. And next lesson, I will explain more in details about why S can hold 2, P can hold 6, and D holds 10, and how are they related on the periodic table.